So we started talking about the different types of algorithms, the two broad categories of algorithms, the greedy and dynamic programming. And we said that the two requirements, perhaps to some extent for both of them, are the optimal substructure, which is for both of them, and the overlapping subproblem aspect has to be required for dynamic programming. So we'll take a closer look at both of these today. And let's take a look at the optimal substructure for the shortest path problem, which we sort of looked at in an earlier lecture in sort of an overview look, and we didn't do a slightly better formal proof of this for shortest path. So let's just do that. And earlier we had said that if you had an optimal solution going from A, B, D, E, G, which was shown earlier in the tan line, and we said that any subpath in the optimal solution is also optimal, which is essentially a reiteration of the optimal substructure property. So let's take a quick look at a slightly more formal proof of that. And this relies on one of the techniques that we have used in the past, which is cut and paste. Does anybody remember where else did we use cut and paste proof? We have used it before. So it wasn't on the shortest path problem yet, but it was on one of the earlier graph problems. Does anybody remember? Well, just think about which other problem did you look at in graphs. We had shortest path, but before that we went through. Yeah, spanning tree. And did we use cut and paste in that? Remember, we had graph, and we looked at both the type of algorithms, prims as well as Kruskal's, and I think in both of them we used cut and paste. Came in handy in both of them. Okay. So cut and paste comes in really handy when it comes to proving most of graph algorithms, and it does come in handy when we're trying to prove the optimal substructure for the shortest path algorithm. The proof is it's almost trivial. If you look at the previous example, it's almost a trivial extension of that. And we're saying that let's assume that PUV is a shortest path between U and V. So here's U and here's V. And remember my notation, something like that implies that it's a path. And if it's a direct edge, then it's shown as a direct straight line. So these are paths, and we're saying that U all the way through X and Y through V is a shortest path. There could be other shortest paths as well. And we're saying that if delta UV, which is the shortest path weight from U to V, is equal to the path weight from U to V, then that is simply equal to the sum of these three individual weights. Right? Obvious. Now, if this is the optimal shortest path, and we're trying to say, well, if the optimal substructure is not followed, then we can assume that, let's say that we have some vertices X and Y in between, whose path weight is less than the path weight from on the original path. Okay, so P prime XY is less than PXY. In other words, this is not following the optimal substructure property. Well, to be able to show that would be a proof and would be a contradiction. So all we have to do is simply cut this path out and replace it with what we think is a shorter path. And then the new path, which now comprises of the other alternate path, so P prime XY rather than PXY, well, this would have a shorter path. Okay, so the cost of this would simply be replacing the middle term over here. And whenever you see a sum sum of individual terms, then it's clear then that there is going to be an optimal substructure. So we're going to replace this, and we can clearly see that this is going to be less than the original, which becomes a contradiction. So it's a formal proof. It's a fairly trivial extension of what we intuitively understood. So that's important to be able to say that there is an optimal substructure before we can do any of the other proofs, which was we looked at Bellman-Ford proof of correctness, and there we used the path relaxation property. And I'm not going to go over that. However, the path relaxation property was in turn based on the convergence property. Okay. So let me repeat the convergence property, because while the path relaxation property was used for the Bellman-Ford algorithm, however, convergence property is going to be used for Dijkstra's. Okay. So the convergence is a little easier as compared to path relaxation. So in the convergence property, we went through this quite extensively in, I believe, the last or the previous lectures. We said that, well, let's assume that you have S to U. All right, so S going all the way to U to V. This is A shortest path. Okay. And U happens to be the last vertex before V on that path, on that shortest path. And we're saying several conditions that S through U through V is a shortest path, number one. Number two, we're saying U is the last vertex before we get to V, number two. And then the third thing we're saying is that the estimate to U, which is U dot D, is also equal to the shortest path weight till U. Three things. And if those three things are true, and in addition, we perform a relaxation between U and V, all right, so now we've done quite a few things. Then we're saying that once we do this relaxation, then the estimate to V is actually now going to be the shortest path weight to V. Okay, so this is just a repetition of what we covered earlier, and it is perhaps a little tricky. There are several conditions before we can say that the estimate to V is going to be, in fact, the shortest path weight to V. Okay? Requires a few prerequisites. So that is the convergence property, and now that's going to be used in Dijkstra's proof. So if everybody remembers this convergence property, let's go on. And now I'll initially sort of give you an intuitive explanation of the correctness of Dijkstra before we get to the formal proof, right? And it basically relies on the proof of the following invariant, the loop invariant for the loop which goes from line 6 through 12 of the Dijkstra algorithm. And essentially what we're saying, now just to remind you, because we have covered several algorithms, so it's good to remind ourselves what Dijkstra was as compared to the other algorithms. Well, in Dijkstra, we had an initial set S, which was initialized to 0, okay, which I'm showing over here. And it had another set Q, which was actually a priority Q, which is everything V minus S was Q, all right? However, that was a minimum priority queue. Why was that? Because it was using the estimates to all of these vertices to create a minimum priority queue. And then we did an extract. So essentially U is being extracted. This particular vertex is being extracted from this priority queue. And when we're doing an extract, we're also pulling it out of Q. Okay, so Q no longer has U. And then we are making a union out of S. So we're combining it into S. So U basically is going to go into S. And how are we selecting U? Well, it's the minimum estimate in all of the vertices in Q. Okay, so U has the minimum estimate. So for example, I've shown you another vertex V, which has a different estimate, which is larger. So here I'm showing you U, which has a lower estimate. It would be other vertices, X and so on. And so U is selected based on its minimum, its estimate being the minimum in Q. And now, essentially, this loop variant is saying that if once U is selected based on its estimate being the minimum, then it's going to be combined into S. And so the loop invariant says that for all vertices V in S, the estimates are in fact equal to the shortest path weights. Okay, so all estimates in here are going to be equal to the shortest path weights, which is not true for the vertices in Q. Okay, so this is the loop invariant, and that's what we have to prove. Is there a question? So if that's the loop invariant, how should we go about it? And can somebody sort of see this? Seems to be maybe perhaps obvious, but can somebody try to make, try to intuitively explain why that loop invariant is going to be true? And remember, when we have a loop invariant and we're trying to prove that, what are the steps to be able to prove the loop invariant? We've done this quite a few times during the semester, right? How do we prove a loop invariant? And a hint is that it has 3 parts to it, right? I can ask Logan, but I'll ask somebody else. Yes, go ahead.
So we check the initial condition to make sure it's true before the loop does.
Yeah.
And then check to make sure it's true.
Yeah, exactly. So those are the 3 steps, excellent, that will be required to prove that the loop invariant is true. So the initial condition, the initial situation is fairly obvious because it starts off with S being 0, and we simply insert the source node over here. So it's trivially true, but the tricky part is how do we ensure that it's maintained? Okay, so we're going to initially have an initial guess, and we're going to make an induction hypothesis. And then we're going to see, well, if we go through this loop, is that maintained? Okay, in the next iteration, is that in fact true? But even before that, as I said, intuitively speaking, forgetting about going through the loop invariant and proving it formally, but can you just sort of look at this and see why that should be true? In other words, if the estimate is the minimum, and here I've shown you an estimate which is larger, then if U is taken from Q and inserted into S, then essentially what I'm saying is that U dot D is going to be equal to the minimum shortest distance from S to U. Okay, and is that intuitively obvious? And if so, why not? Why not? Why? So, just taking a look at this particular example. So you have U, which has the shortest, the estimate is 10. The estimate over here is 20. In other words, to be able to go from S to any vertex in Q, in this case, there are 2 possible choices. You could go to U at a cost of 10. You could go to V at a cost of 20. Okay. So if you chose U, then why would the estimate be the shortest path? Why can't we say that, well, we could perhaps go through this path, or we could go through this path and come up with a lower estimate or lower cost to get to U? Why would that not be true? Perhaps what conditions would that be true? Yes, Ibrahim. Yeah. So you said a very important point that, and that would be the only case where this would not be true. In other words, if you had a negative weight over here, if this was -5 or rather -15, let's say, then in fact, this would not work out. And that's why Dijkstra doesn't work with negative edges. Okay, Dijkstra only works with positive edges because it's making the assumption that if you found the weight over here to be lower than the weight over here, then if you're going through this path, and unless you don't, and if you have all positive weights, then to go from V to U is going to add on some further cost to going from this path. Okay, and if this is already higher, and yet you're adding another positive edge, it's going to be even higher. Okay, so it's clear that this would in fact be the shortest way to go from S to U. Okay, in which case the estimate at U would in fact be the shortest path weight to get to U. Okay, so that is the intuitive explanation, but we need to do a slightly more formal proof for this. So and this is, I'm just repeating what Rose said, that this will only not be true if there was a negative edge. So let's take a look at the formal proof, and it has several steps. So we'll go through these one by one. And so the first question is, what kind of proof do you think we can come up with? We've looked at cut and paste. And I said, so far, actually, we've only used cut and paste proofs in all of the graph proofs, right? And would cut and paste work over here? You've got several examples of cut and paste, right? And that's generally the easiest proof. The first question is, can we use a cut and paste technique to be able to prove Dijkstra's algorithm? Something to think about. Can we use cut and paste to prove Dijkstra's algorithm? In other words, we saw how cut and paste worked over here. So we saw that you had a sum of path weights, and if the optimal substructure is being followed, then we could replace one of the path weights with a lower weight. That would be a contradiction. So could we use cut and paste in Dijkstra? So if you are confused about that, the answer is that you can't. Okay, and that's perhaps why you can't think of a cut and paste proof. Okay, so and that's why we had all of these other lemmas about relaxation and path relaxation and convergence. And so we're going to use those. So again, here's what we're trying to prove. This is the loop invariant, which is we're saying that for all vertices V in S. So I've shown this using the graph, using the diagram from the book. And S is shown here in blue. These are all the vertices which are already in S. And we're essentially saying that we need to prove that all the vertices in S, their estimates are equal to the actual shortest path weights, which basically means that if we can prove the following, which is line 7. So as soon as we extract U, then U's estimate is the shortest path weight. And if we can prove this, then this automatically is proven. Okay? Because U is being pulled out from Q, it's being inserted into S. So we're going to make an induction hypothesis, and we're going to say that we'll assume that for all the vertices already in S, the following is true. Okay, for all the vertices already in S, we're saying that the induction hypothesis is that those vertices already have the following property, that their estimates are already equal to the shortest path weights. Right? And I'm going to throw some numbers over here just so that you can see some concrete numbers as you're trying to go through this proof. So we're trying to prove that these two are equal. Okay, in other words, U of D, let's say, is 100. We're trying to prove that, and if the shortest path weight is also 100, we're trying to prove that U of D will be equal to 100 when we pull out U based on line number 7. Okay. So in order to prove that, we're going to do a proof by contradiction. And the contradiction will be continued as follows. We're going to start with making an assumption that let's assume that U is such that it is not, okay, it is not the shortest path weight. All right, so now I've changed U to be slightly larger. So I've taken the shortest path weight was 100 delta, and let's assume that U is not the shortest path weight, it's some number larger than delta, which is, let's say, 120. Okay. And without loss of generality, we can say that let U be the first such vertex which is added to S. Okay, so we're going to say that U is the first such vertex which is going to be added to S, which has this particular property of not being the shortest, its estimate not being the shortest path weight. Now, we're going to look at a particular path, and we're saying that, well, let's assume that there is another path, okay, which is going through Y. And remember, this can be true if there is a negative edge. So if this was negative 15, then in fact, this could be true, but these negative edges are not allowed. So let's assume that there is another path, okay, there's another vertex, Y, which takes us to U, and that is the shortest path, okay? So, and now we're going to look at X and Y, and we're saying that Y is the first vertex on the shortest path from S to U. So here's a shortest path, which is not going to U. So it's not going directly to U, it's going through some other vertex Y. Okay. And this is the shortest path, maybe taking a loop back into S, but we can neglect that. And we're saying that X is the last vertex in S, which connects to Y. Okay, so this path goes from S to X to Y to U. S and X are inside S, and Y is the first vertex outside of S on that particular path. Okay. So I hope this particular picture is clear. And you're clear about the path that we've taken. So if that is clear, let's go on. So now we're going to make a number of statements which are all going to lead up to this contradiction. Okay. So from line 1, from line 7, we've seen that U must have the shortest path estimate. Okay. So U dot D and Y dot D clearly must have a relationship in that since we've picked U, and that is coming out from the min priority queue, which has the shortest, which had the lowest estimate, then clearly the estimate to Y must be larger than U. Okay, or perhaps at least equal to U. So you have U dot D has to be less than Y. Okay, so this is a problem. So now I've made Y to be some number larger. Okay, so I've chosen Y to be, let's say 130 instead of, which is bigger than the estimate at U. That's the first point. The second point is that if we have Y on the shortest path to U, okay, then the weight to get to Y, unless you have a negative edge, if all the edges are positive, then the shortest path weight to get to U must in fact be greater than the shortest path weight to Y. Okay, because you're going to Y, and then you're going to U, you're adding positive weights. Okay. So delta SY must be less than the delta SU. Okay. So I've picked a number here which corresponds to that. So 80 is now less than 100. Okay. So hopefully you can already start seeing what the possible problem is. Can somebody now start seeing what could be the next steps? So we've said that this has to be greater than this. That's a property of relaxation. Yeah, that's a property of the estimates. The estimates start at infinity and they go all the way down till delta. All right. We're saying that you have this is smaller than y, than the estimated y. Okay. And we're also saying 80 is smaller than 100. Okay. And now somebody see what could be the next possible step in this proof. Can somebody sort of see where we're heading with this and why this could lead to a contradiction? And now think about, I've already given you a hint that we're going to use the, not the path relaxation, but the convergence property, okay? Who remembers the convergence property that we just spoke about? What does the convergence property say? No, Logan, you repeated that last time, almost accurately. So can somebody else repeat what the convergence property is? And I'll show it to you again. So this is what the convergence property says. It says that if this is the shortest path, U is the last vertex before V, U is already, its estimate is already the shortest path weight. Then if you relax U and V, then V has to be equal to the shortest path weight. Okay, bit of a mouthful, but I hope you got that. So if you understand and if you've digested what the convergence property is, okay, then can you sort of see where we're heading with this? Okay, so can you see how the convergence is now going to be used? We're saying that X is inside S. So it satisfies one of the requirements that it has already achieved X dot D. The estimate X dot D is already equal to delta. All right. Why? Because that was the induction hypothesis. We're saying this is already on the shortest path. If it's already on the shortest path, and if this particular path has been relaxed, then what does that imply? What does it say about Y? The estimate Y. If this was on the shortest path, if X has the value of delta, if this was relaxed, then what does it say about Y? The estimated Y. What does it say about the estimated Y in comparison to delta? Yeah. Yeah, that's exactly what the convergence property said, that as soon as those conditions are true and you do a relaxation, then the delta at the estimate at Y is going to be equal to delta. Okay. So now can you see the contradictions that are coming in? So can somebody, before I just show you the proof, you should be able to see it from now. Okay. So now we're saying that this has to be equal to the delta value because this is being relaxed. And so now this is going to be equal to 80. Okay. So do we have a problem? Yeah. Yeah, so you can see the problem coming up, right? Because we're saying that the estimate over here was chosen because of the fact that it came out of the minimum priority queue and it was the smallest estimate. And now we're saying that this has to be greater than this has to be greater than this, and these two are equal. So now you can sort of see where this is leading up to. And you can see that we're going from delta. This delta has to be smaller than this. This has to be greater than this. This has to be this has to be smaller than this. And so we've got a problem. And you can just follow this logic and you can see that all of these are going to imply that delta SY, okay, has to be equal, has to be less than Y dot D, but these guys are in between. Okay. So this is less than this, is less than this, okay, which is less than this, all right, which implies that what does it imply? If all of these, if the starting point and the ending point, y dot d, we've already said that y dot d is delta sy. So we're saying that these two, the starting and the end, are the same, and you've got a less than equal to property in the middle. What does that imply? What does this imply? Yeah, that they're all equal, right? That this less than equal to is in fact going to be converted into an equality. Okay. So essentially we've got the following statement, and hence we've essentially proven that now u dot d, which was coming in the middle, is now equal to delta su. These two are now going to be equal. Okay, so what we're saying is that if we had picked u based on the minimum priority queue, then there is a possibility that there is, because remember, there can be multiple shortest paths. Okay, so if there is another shortest path which goes through y, then the only possibility of that happening, if you don't have any negative edges, is that there are two shortest paths. Okay, and that you can go through y to get to u, or you can go directly to u. Okay, and there could be multiple shortest paths, but they all have the same weight. So there was a bit of a perhaps lengthy proof, but at least it didn't involve probability. Okay, but in graphs, the proofs are a little different. So you don't involve probability, but you look at the graph and you sort of make individual step-by-step statements. You have lemmas and so on, and it's a different type of. I don't know if you like the probability proofs more, or you like the graph proofs more. So I think most, Kyle is probably speaking for the rest of us that the probability proofs are probably not as favorably viewed as the graph proofs. Okay. But we are going to get back to the probability proofs before we finish the semester, unfortunately. Okay. Right, so we've done the proof of correctness of Dijkstra, and we're done with that. And now let's continue on from where we left off, talking about the all pairs shortest paths. Okay. And we looked at the Floyd-Warshall algorithm, and we looked at this, had a quick overview of this, but we'll sort of look back at it and try to see if we can sort of analyze this and see how does it perform, what are its complexities, how does it compare to using one of the single source shortest paths and simply repeating that v times. Okay, so is Floyd-Warshall actually better than those? Not. Okay, so just to review what we did in Floyd-Warshall was that we said, well, we're going to assume that we have the shortest weights, shortest path weights from I to j. We have estimates, and we'll see if we can improve those estimates by going through all other vertices k, right? And we did this, we initially said, well, can we go through one and make it better? And then we said, well, can we go through vertex 2 and improve what we did? We already achieved going through 1. Okay, so we've already achieved 1, and now based on the improvements in 1, can we now improve by going through 2? And then we said, well, now we've done these 2. Can we now go through 3 and look at our best results in the past, and can we improve on that? Okay, by going through vertex 3. And then we said, well, we've got 3, the best solution, having gone through 1, 2, and 3. Can we improve on that by going through vertex 4? And we saw that there were several improvements. And then finally, we're going through vertex 5, where we say that, sorry, this is supposed to be highlighted over here. So we're going through vertex 5 now, and we're saying that can the estimates be improved. And clearly you can see that starting from D0 to D5, we've got quite a few improvements, right? So I've highlighted all of these improved paths. So we have the shortest path weights, and we've got the predecessor matrix. And so you can see that in the earliest, at the starting point, when you start off at 0, a number, most of these were nil because we didn't have any shortest path. Having gone through 5 of these iterations, we go through a maximum of V iterations. That's the number of vertices. And you can see that now we have a whole bunch of improved shortest path weights. And initially, if you had infinity, then if it's improved to some value which is non-infinity or less than infinity, then clearly you have a way to get to that particular vertex. And this can also be seen as a reachability matrix. Okay, and we'll come back to this in a little. So this gives us a shortest path weights. And if we now try to look at the actual algorithm, so that was an overview of the algorithm, but if you try to look at it slightly more formally, so this is what we did. We started off by making the initial estimates to be equal to the initial adjacency matrix, adjacency weights, okay? And then we said, well, we're going to start from k is equal to 1 through n. So this is where we're saying we're going to try out all the other vertices, try to go through k, okay? K is some intermediate vertex. And we'll see whether we can improve the estimates. And the way we said, well, we'll look at each one of these for every value of I and j. So for I is equal to 1 to n, for j is equal to 1 to n. For each one of these, we're going to see whether this particular statement is true or not, and can we find a minimum value. So what are we doing in each one of these cases? We'll be saying that we're looking at the earlier matrix. So for D1, we're going to look at D0. And we're going to say, well, is there a better way to get between, let's say, 1 and 4 by looking at the original weight, okay, which is what this is. All right, looking at the earlier matrix, going from I to j. Is this better, or can we get a better path by going through some intermediate vertex k? Okay, so k happens to be the same over here in the numerator as well as in the subscript. So we're going through some alternate vertex k, and we're saying, well, if we add the path through k, can we find a shorter path? And if that is true, then we're going to update the matrix. Okay, so this is exactly what we did in the last lecture, and at the end you return the final value of d. Okay. So that was a fairly simple code, I hope. You can see that that's nothing tricky about that. It's a fairly simple going from the high-level understanding of Floyd-Warshall to actually looking at some pseudocode. That's hopefully straightforward. Now the questions are time versus space complexity. Okay. So what do you think the time complexity is on Floyd-Warshall? And if you look at these loops, k is equal to 1 through n, I is equal to 1 through n, j is equal to 1 through n, and then you have a statement over here which is hopefully kind of obvious. So somebody else, what would be the time complexity? Floyd-Warshall, yes. Sorry, say that again. Cube in small n, yeah. So it's going to be order of n cube. Kind of obvious, right? Everybody can see that? Simply because we have 3 for loops, they're all going through 1 through n. Okay, put that as a theta. What would be the space complexity? Somebody else. What would be the space complexity? Holding on to you guys. Somebody else, what do you think would be the space complexity? Now, think back, the way we did it is that we went through all of these matrices, right? We started with D0, and we can forget about pi 0 for the time being, but we went from D0 to D1 to D2 to D3 to D4 to D5, right? So what do you think the space complexity is going to be? Somebody right in the back, yeah. all of n squared. And why do you say that? But that 4 is based on what? We did 5 iterations, but we only did 5 iterations. Why? We did 5 iterations because that was the number of vertices. So in fact, if there are 100 vertices, we would do 100 iterations. Okay. So, so now can you revise your answer? In other words, we have each matrix is of size n squared. So clearly we're going to take space n squared, but we're keeping track of how many matrices? We're keeping track of V matrices, right? Because if there are V vertices, then we're going to keep track of another n. So it seems like it's going to be n cubed. Would you agree? Because now we have n squared, each matrix is n squared, taking up space n squared, and we have n of those, so it's n cubed. But is there a better answer? Yes.
So you need to keep track of.
Yeah. So we only actually, this algorithm doesn't show you that. All right. It's sort of saying that let's keep track of all of these. But if you can just sort of see through that, that you never used any of the earlier matrices, right? So when you look at D5, so when we looked at D4, for example, you're only using D3. So we could have thrown away D0, D1, and D2, right? So essentially, we don't need to keep track of all the matrices, and so we can reduce it to n squared, right? So hopefully everybody sees that. Yeah. So we've got order of V cube for time, order of V squared for space. Now, how do you think this compares with if we did sort of a brute force method in which you used either Dijkstra or we used Bellman-Ford, and we tried to use it for all of these? We applied the single source and we repeated it for all the V vertices. So which one would you think is better? Yes. Yeah. So remember, Dijkstra actually did E log V. Okay, Bellman-Ford did V times E, and Floyd-Warshall seems to be doing V cube. So now you have a matrix of possibilities, and let's try to fill this out. Okay, can somebody give me suggestions for each one of these boxes? So let's start with a sparse matrix, and assuming that all of the edges are positive. Okay, so what would the Dijkstra complexity be? And we're just looking at time. Okay. Yeah, so we're going to do another multiplication by V because now we're applying Dijkstra for all the sources. So it's going to be V times log V. So that's what we have, right? So V squared log V. If it's dense and positive, then clearly E is going to become equal to V squared. And so that's going to become V cube log V. Is that right? Yeah. Sparse and negative can be used. So we can't use Dijkstra for whenever you have negative weights, regardless of whether you have a negative cycle or not. Even if you have negative weights, you can't use Dijkstra, as we saw earlier, okay, in the proof. Now let's look at Bellman-Ford. Can somebody tell me? Yeah. What would be the complexity for sparse? Somebody else. Somebody else. Yes. V cube. V times V times V. So that's V cube. Clearly because E is going to be of the order of V. That's clear. And if it's dense and positive, dense and positive, yes. V to the 4, yeah. So that's going to become V to the power 4 because E is already V squared, and you have two more V's, so it becomes V to the power 4, which is not looking very good, right? What about sparse and negative? Well, it already does, it should be the same, right? I mean, it actually does positive and negative. So we can just copy this. This is going to be cube, and this is going to be V4. Okay. What about Floyd-Warshall? We can neglect this portion because, might as well just focus on this portion for these two algorithms because they are working basically with negative edges, and there is no advantage if you just had positive edges. So what would be Floyd-Warshall? Well, that's simply V cube. Okay, regardless of whether you have a sparse or even a dense graph, it still does it in V cube time. Okay, so for each one of these columns, can we now decide which is going to be the best algorithm? So if you had a sparse and positive graph, the best algorithm seems to be what? So this is also V cube over here. And clearly V squared log V should be the best. Okay, so Dijkstra is the best over here. What about if you had, this is V cube. Okay, so Dijkstra is clearly suffering over here. So it seems like if you have a dense and positive, okay, or regardless of whether it has positive or negative, if you compare these two scenarios, if you have a dense with positive or negative, then clearly Floyd-Warshall is actually the best. Okay, you can't apply Dijkstra, and Bellman-Ford becomes V to the power 4. However, for sparse and negative, they both seem to have the same complexity. All right, and so then other factors will determine. And generally, what the rule of thumb is that if it's a dense graph, then generally Floyd-Warshall is used. Okay, so those are the pros and cons of this particular algorithm, and so we can basically see that it is best for dense graphs. Okay. I mentioned this earlier as well, the reachability matrix. So that's also called a transitive closure on the graph. Okay, so the Floyd-Warshall can also give you what is referred to as a transitive closure. Okay, what that basically means that if you look at the final matrix D, and if any one of these values is non-infinite, which is less than infinity, then it implies that there is a reachability between those two pair of vertices. Okay, so if you have a -3 over here, that implies that you can go from 1 to 3 and so on. So in this particular graph, you have complete closure. In other words, you can go from every vertex to every other vertex. But that's not always true. And so if you had a different set of results in which some of these, for example, were infinite, all right? So in that case, it would also give you a transitive closure on that problem, and it will tell you whether some vertices are reachable or not, right, from other vertices. So between I and J, it will tell you whether J is reachable from I or not. And this also tells you the actual weight. But if you just wanted to find out the reachability, you could just treat that as some number less than infinity. So these are some of the pros and cons and some of the advantages of Floyd-Warshall. And the final question is, if you think about where we started off from in today's lecture, we said, well, there are two broad categories of algorithms. There's the greedy algorithm and there is the dynamic programming algorithm. Which type of algorithm do you think this is between those two? Does it seem to be a greedy approach, or does it seem to be a dynamic programming approach? And I didn't really talk about too much about dynamic programming, and that's what you're going to do next. Yes. Yeah, so you're using past results and you're sort of building up on that. And the greedy approach basically says you look for a locally optimal solution. And there is no locally optimal solution. You're actually looking for all possible paths, right? And you're building up on past results. So those are the things which sort of indicate to you that this is a dynamic programming approach. Okay? So that brings us to the question is of what is dynamic programming, right? And so this is normally covered earlier, but I thought that it would be better if we looked at some examples of how dynamic programming algorithms actually work. And then if we look back at trying to understand dynamic programming, then it would perhaps make more sense. So it uses dynamic programming. And so let's try to see how dynamic programming actually works. And so in order to look at this, I mentioned that the Fibonacci series was one example of how dynamic programming sort of builds up on past results, could build up. But Fibonacci series is not a very good example, simply because there's a much simpler iterative solution to that. And so we'll take a look at a different problem. And we'll take a look at something called the rod cutting algorithm, or the rod cutting problem, okay? But we're going to keep track of the following two properties. So in a dynamic programming algorithm, you must have an optimal substructure, number one, and you must also have overlapping subproblems, okay? So let's take a look at another class of problems, the rod cutting problem, and see if we can see the dynamic programming properties here, right? So what is the rod cutting problem? The rod cutting problem basically says that let's assume that you have a rod of length I, right? And you can cut it up into smaller pieces. And each one of those smaller pieces has a different price. You can sell those at different prices. And they're not necessarily linear. In other words, for example, if you have a rod of size 1, then let's assume that it fetches you a price of $1. But if you have a rod of size 2, then that is much more perhaps in high demand, okay? And that gives you a much better price. It gives you a price of 5, all right? If you have a rod of size 3, then it gives you somewhat better results as well, okay? So it's clearly not equal to the sum of its individual components. So if you took a rod of size 2 and cut it up into 2 smaller parts, each of them individually would only give you $1 each, all right? So that would only fetch you $1 plus $1, that would be $2. But in fact, if you kept it at a size of 2, then that has a much better price, okay? Simply because people have different demands for different rods, and you can't just combine them together and use that. So once it's cut up, it uses some value. So the prices in this particular example, this is again from the book, are increasing, but they're not linear. All right. So for a rod of size 3, the price goes up. It fetches you a better price. 9 is higher than 8, and so on. So these are going up. But sometimes, for example, if you have a rod of size 6 or you have a rod of size 7, they both fetch the same price, right? Why could that be? Because that clearly says that when you're going from 5 to 6, that shows you that a rod of size 6 is in high demand. But if you go to 7, nobody wants that. Okay, probably what they're going to do is take a 7 and they're going to cut it down to 6, and they're going to use that, right? And that's why it doesn't fetch you a higher price. So that extra 1 inch is not getting you anything, 1 inch or 1 foot or whatever metric you're using. Okay, so you have a general idea of the rod cutting problem. Now, the question is, if you have a rod of, let's say, a particular size N, all right, then how would you figure out what's the best way to cut it up, whether it needs to be cut up, or what's the best way to cut it up so that you can maximize your revenue? Okay. So does that seem to be an easy problem, or is that a difficult problem? So if you think about categories, complexities of different problems, how would you intuitively guess the complexity of this particular problem? Is it constant? Clearly not. Is it order of n? Is it order of n squared? Is it polynomial in n? Or is it more like an exponential? Not Kyle, the gentleman in the back. Okay, so n squared, if not better or not worse? Okay, so it could either be n or n squared. You're saying that it's probably order of n squared. Okay. Interesting. Somebody else. Then I'll get to somebody else. So now think about the following way. You have, let's say this is of size n. Okay. How many possible ways can you cut this up? How many possible cuts do you have? So the cuts are at integer intervals. Okay. You can't cut it up at 1.5. You can only cut it at 1 or 2 or 3, going all the way up to n. Okay. So how many possible cuts could you have? I've already shown that. It's I minus 1. Right? But what are all the possible combinations? So if you want to look at the solution of this particular problem, what are the possible solutions to that? How many possible solutions could you have? And if you're doing a brute force method, you'd have to look at all the possible solutions, right? So what are all the possible solutions, Jane? To the power of n minus 1. Yeah. So at each one of those intervals, you have a binary decision, right? It's either cut or no cut, right? So if you had 2 possible cuts, you could have to the power 2, 4 possible solutions. If you have 3 of these possible cuts, then you could have 3 possible combinations, to the power 3, that's 8. And if you had n minus 1 possible cuts, and you could have all possible combinations of those, then clearly Jane seems to be right. You could have a possible explosion of solutions, which is essentially an exponential problem. Okay, it's not a polynomial problem. It's 2 to the power n, and if you remember, 2 to the power n, that is a pretty bad complexity. All right, so this is about as bad as you can get. Maybe n to the power n is worse, but 2 to the power n is close to being one of the worst complexities that you can have. So this is clearly a much more a serious problem as compared to the Fibonacci. And that's why this is a more useful algorithm to look at when you're looking at dynamic programming, because Fibonacci series had a very trivial solution because it was just dependent on the last 2 sums. Okay, and you could just save the last 2 and have a great solution. But this is clearly for a different category. So you could have, so this is another illustration of the problem. So for example, if you had a rod of size 4, then you could have no cuts, okay? And the cost, the price, the revenue from that particular rod would be just 9. But if you cut it up over here, okay, and if you had a 1, price of 1, and 3, a price of 8, so that would be 8 plus 1, 9. That would give you, if you cut it up into these 2 pieces, it would still get you a revenue of 9. However, if you cut it up into 2 pieces, which are both of size 2, and this seems to be more profitable, right? Because a rod of size 2 sells at a nice price of $5. So you get a 5 plus 5, that's $10. So you sort of increase your revenue by cutting it up into 2 smaller pieces. If you cut it up into any one of the other combinations, and you can hopefully see that there are, in this case, to the power 4 minus 1, 3, 8 solutions. 1, 2, 3, 4, and that's 8 solutions. So some of those solutions are, of course, redundant. They're repetition. So you can see that B and D are essentially the same solution, just a different permutation of that. Okay. But some of those solutions get you a higher revenue, right? So this one is getting you a higher revenue. The other ones are perhaps a lower revenue as well. This seems to be the worst. Okay. So the question is, can we convert this into an algorithm using the concept of dynamic programming? All right. But in order to be able to apply dynamic programming to this, we first need to see whether it has those 2 nice properties, which is optimal substructure to start with. Okay. So in this particular case, as I said, this would be the optimal solution, which would be to cut it up into 2 small pieces. And so we've already addressed some of these issues, that the possible solution size is of the order of 2 to the power n. So does it have an optimal substructure? If you have a problem of size n, okay, and let's assume that you have an optimal solution which says, let's cut it up over here, all right? Then the smaller problems, would these in fact be, if this was a solution to S, so S1 and S2 comprised of the solution to S, then do you think that S1 and S2 themselves be optimal solutions? That's what optimal substructure says, right? That if you have an optimal solution, then the subproblems of that would also be optimal. Okay. So think about this. Would the rod cutting problem have optimal substructure or not? Somebody can think. If it's yes, then you'll have to prove it as well. And you have to think about what technique would you use to prove this. Now, so far, we've seen at least, we've seen a whole bunch of techniques actually to prove algorithms, starting with, all the way from going from, quick sort and merge sort. We saw, the divide and conquer method to cut and paste to, proof by contradiction and so on. So does anybody have any clue? Do you think, well, you don't have to prove it right away, but do you think it has an optimal substructure? Yes. Okay. And can you sort of try to explain why you think it has optimal substructure? Mm-hmm. So you're saying if let's say R3, the revenue from R3 and 1, 2, 3, 4, 5 and R5 were in fact the optimal solutions. Okay, and the sum R3, R is the revenue that's being generated from a rod of size 3, and R5 is the revenue being generated from a rod of size 5. So if R3 and R5 are part of the optimal solution, let's assume that you have the optimal solution. Then the question is that would the solution, the subproblem, R3 that comprises of the optimal solution, would that itself be optimal or not? And you can sort of try to think about whether what happens if it wasn't optimal. Okay, so if S1 wasn't optimal, and there was another solution S1 prime, which was in fact the optimal solution to the 3-rod problem, rod of size 3, then what does that indicate? And where is this proof heading us? Okay. Yeah, we're saying that that is an optimal solution. So we're starting with that assumption. Okay. Yeah, so what kind of proof are you basically hinting at? Is this like, is this remind you of any of the other types of proofs that we've just looked at in today's lecture? So you're cutting proof by, you're cutting this guy out and you're replacing it with another possible solution, which is, let's assume by contradiction that we have another solution which was better, but it wasn't used as part of the solution. Okay. So here's basically what we're saying, that so we're saying that the optimal solution S must incorporate sub-solutions which are also optimal. Okay, that's what basically what we're saying. And the proof is basically a proof by cut and paste. Okay, so let's assume that S1 was not optimal. Okay, and S2 prime, sorry, this one, let's say that S2 is not optimal and S2 prime is better. All right, then we could simply remove this from the solution to S. We could replace this, and then we would have a better optimal solution to the overall problem. Okay, so if S2 prime were the optimal solution, then we could cut out S2 and replace it with S2 prime and hence improve S. Okay, so then S would not be the optimal solution. So if S did not comprise of suboptimal solutions, then in fact, there would be a problem. Okay. So hopefully you can see that it does have the optimal substructure. Once again, you can sort of see that it's sort of an addition, right? You're simply adding up things. The only other example where I gave where you didn't have an optimal substructure was, can somebody recollect the example that I gave where you don't have an optimal substructure? So way back when you're looking at minimum spanning trees, and it said that there are some problems where you don't have optimal substructure. And yes. Yeah, sites, because it's not a simple sum. If going from Chapel Hill to New York to LA, then the cost to go from Chapel Hill to LA is not simply a sum of those two. Okay, that's not how pricing in the real world works for most cases. So so whenever it's a simple sum, you can see that the optimal substructure is followed. So we do have a few more minutes. Let's keep it going. So now let's try to, just try to understand the problem better. And let's do a little bit of, exercise to see if we can come up with an optimal solution. So can somebody tell me what the optimal solution is if you have a rod of size 2? Would you cut it up or would you just leave it as it is? And what would be the revenue from a rod of size? Well, for revenue from rod of size 1 is just 1. What's the revenue from a rod of size 2? 5. So that's $5, and there are no cuts, right? Because if you cut it up, you would only get $2. If you had a rod of size 3, what would be the optimal solution? So it would be 8, and there would be no cuts, right? Because if you did cut it up, you would get 5 plus 1, which is 6, which is less. What about size 4? Well, we've already done this. Then it's going to be a revenue of $10, and you cut it up into 2 plus 2, right? You get 5 and 5. What about a rod of size 5? Can you find a better solution, or is 10 the best? And what's the solution? What? 13 is based on what? 3 and 2. So 8 plus 5 is 13. So we do 3 and 2. These are the sizes that we're cutting up, and so on. So you get the idea, right? So if you have size 6, then probably 17 is the best. And this is just an example from the book. So you can see that it does become more and more complex as you go forward, unless you have the previous solution. So if you went in this particular order, then how exactly are you forming the solution? Can somebody sort of now visualize how we're forming the solution and what data are we using? So we've got two sets of data. We've got the original table, which for each length, it had a price. And then we have another optimal solution, which is the following table. Okay, so can somebody tell me how we're actually, how would you, as you're going forward, what were you actually doing? Were you looking at the table over here? So when you said 8, we looked at a rod of size, let's say 8. Okay, so sorry, let's look at 5. So we said that 2 and 3 are better. Okay, so did you look directly over here, or did you look over here? And which would be a better way to look at the problem? Where should we look? Yes. So where are you actually looking for the data? That's my question. In the first table or the second table? In the second table, right? Because the second table is actually already got the optimal solutions. Okay, so we already have the optimal solution for 5. And so we're not going to, when we're looking at 8, we're not going to go back to the original table. We're actually going to look at the recent results. Okay, and that sort of builds up on the dynamic programming approach. We've already seen that in some of the other algorithms, that as you're building up the solution, you're going to start looking, you're going to save those solutions, and you're going to start using that data. Okay, so so that's the basic idea, and I think that's where we're going to stop, and we shall continue on in the next lecture.